Okay, it's time. So let's start with lecture 7. It's about velocity kinematics. Especially, we're going to discuss in details what do we mean by geometric and analytical Jacobian for open chain. So last lecture, lecture 4, we talked about forward kinematics. As I somehow suggest you should think, at least for this class, a robot is just multiple rigid body interconnected through joints. Okay, and so that's why everything is related to joint variables. I suppose given in this robot, and this is suppose we have a frame on some part of the body here. This is called frame B, right? And the forward kinematics problem that we learned before is trying to find, our goal is trying to find the nonlinear possibility mapping or function of TB, the pose of B, right, as a function of theta 1 of all the way to theta n. It's as a function of the joint variables. And so in other words, given joint variables, there's a mapping uniquely defines or determines the frame B pose. Okay, the result we got from last time is the so-called exponential product of exponential. Liu Ben, what's the result? Can you write down the formula for the pose of B?
Yeah, it's the e to twist 1 theta 1.
Okay. All right, that's fine. Let me finish that for you. Theta 2 all the way to theta n bar theta n times m, where this m is the initial pose. Is the pose when all the theta are 0. You can define whatever the home position or the initial pose, initial position of the joints in any way you want. Okay, and the key is that it's a multiplication of several matrix exponentials, and this one, for example, SI bar, my notation, SI bar in O, what's the meaning of it, Liu Ben?
That means only the theta I. That means the twist 1. The square axis I represented in the inertial frame at all inertial. The initial condition is 0.
Oh, great. So screw axis I, when all the theta I, theta j are 0, all the theta i's are 0, and expressed in O, okay? That's the meaning. Because the screw axis also moves with the joint variables. If you change your joint position, the screw axis move in the space, okay? At least with respect to the fixed or inertial frame. So that's the formula we have learned. And we also gave a trick example to verify that. So that's something that we have learned before. And today we are going to talk about velocity kinematics. So this forward kinematics, so the last lecture is really about the position relation, how the joint position got mapped to the pose of, or the position or the pose of the any factor. Now we care about, velocity kinematics care about how the velocity of the any factor frame, let's call it B, relate to the joint velocities. Okay, that's the velocity kinematics. And you have to know that, note. So if all the joint velocity are 0, in the sense that all the joints are not moving, then the frame B is not moving, right? So the motion of B is solely dependent on, it's only due to theta dot, okay? It's the velocity of the joints. So this velocity is due to joint velocity. There's other things In other words, if all the joint velocity are 0, then B doesn't move. Okay, so this relation so it really depends on how we represent the velocity of the frame B. Okay, so let me ask questions. So this depends on this relation because we want to understand the relation between joint velocity and the end-effector frame velocity. And this relation really depends on how we represent the frame B's velocity. Okay, so can we, for example, typically this is the position, okay? Can we use the derivative of position, in this case, the pose, so TB dot to represent velocity of B? Ruben, do you think that's a good idea?
Yeah.
Yeah?
Oh,
This
no. No, sorry,
no.
no.
Okay. This is a 4x4 matrix. Okay, if you take derivative, this matrix has special structures. It's not good for a representation of the velocity. We know the frame B has 6 degrees of freedom, right? It's x, y, z, and maybe rho PGL. Okay, so that's the 6-dimensional freedom, and its velocity is also 6-dimensional. All right, and one way that we have learned so far, because B is a rigid body, right? It's a frame, is a rigid body, and to represent a rigid body velocity, the way we have learned so far, and we promote and we advocate for this representation is the twist or special velocity representation, right? So in this case, we call that a twist or special velocity, that they are the same. Let's say this is V of B, twist, and it consists of 2 things, right? Omega and V. And this V has a special meaning. I hope you all remember that now, okay? And we know this velocity, as I mentioned, so depends on both theta and theta dot. At least depend on theta dot. If theta dot is 0, then of course VB will be 0, and the velocity also depends on the configuration of the robot. Okay? And it turns out, VB, the twist, is a linear function. So far we know it's not depend on it, right? It's just like the pose of TB, we know it's a function of theta 1 up to theta n, but we don't know the expression. So we derived it last time, but now we know it's a function of theta and the theta dot, okay? But it turns out eventually we were going to show this for you today. It's a linear function of all the theta dot. Okay, so a linear function, we can write it like VB is a function of theta and theta dot, right? In general, the function of theta and theta dot is actually, okay, let me resolve this part. This part is actually a linear function, is matrix times, let's call it theta times theta dot, right? So, and this part, this linear mapping, so this matrix, this is a matrix, all right? And it's the geometric Jacobian. Okay, it maps the joint velocity to the twist of the end-effector frame. Okay, it depends on theta. So that's the linear mapping from joint velocity to end-effector twist. That's a geometric Jacobian. Based on my definition here, although I didn't derive it yet, what's the dimension of this theta, J of theta?
The dimension of this is 6 by n.
Yes, right? It has n columns, 6 rows. That's the dimension because it maps this to a twist. Twist is 6 dimension, right? Another way to represent it is kind of different. we use here geometric Jacobian. By definition, we use twist to represent the anti-vector frame velocity, and sometimes it's more convenient to directly write down quantity of interest directly, and not in terms of twist. We can use some local coordinate of SE3. What that really means is here. So suppose I have the joint variables, then I know the forward kinematics, as I reviewed before, it's a function of them. And this is nothing that has two parts, right? It has R and P, both are functions of thetas. I didn't write the dependence here. And these two things, I can represent them. For example, the R only have 3 degrees of freedom. For example, this can be rho PGL, RPY. Okay, so this alpha, beta, gamma. Okay, and this one is in R3. I can use Cartesian coordinate, maybe X, Y, Z. So overall, each of these I can use one thing to represent it, which is maybe Px, Py, Pz, and alpha, beta, gamma. That's also 60 vector in R6. And so this one is, let's call that maybe X in R6. Okay, so this overall mapping, let's say from here to this X. So given a joint configuration, I know exactly this the anti-vector frame PYP, PX, PY, PZ, the center of the frame, and also the orientation represented by some kind of Euler angles. That's one way, for example. Okay, so this one will be a mapping, is a function, right, of theta. In other words, so that will be let's say X equal to G of theta 1 all the way to theta n. You see what I mean? You can pick different coordinates representations to represent the anti-vector frame's position, right? And now if you have that, then if you want to know this coordinate speed or the velocity of those minimum coordinate, I can take derivative. And this derivative is mainly due to the non-zero derivative of theta dot, right? So it's then I have partial G, partial theta, that's a matrix, that's a Jacobian matrix, times let's say theta 1 dot all the way to theta n dot. Okay, and this guy, for then I'm going to ask you again, what's the dimension of this guy?
Is same as
before 6 by n, right? So this is a matrix. This is so-called Jacobian matrix. For any function of this multivariable function, this one is a matrix. It's let's say partial G, partial theta is a matrix. It's I row J's column equal to partial I, Gi partial theta J. Okay, that's the definition. I hope you are fine with that. And this one is called, this guy, hold on. This guy is called Analytic Jacobian, Analytic Jacobian. Okay, and it contains many information that we may be of interest in. For example, if I purely interest, for example, okay, for example, if I'm only interested in position, the anti-vector frame position, then I know the position is the first 3 elements of X, right? So P is also a function, let's say P of theta equal to, let's say Px of theta, Py of theta, Pz of theta, right? And I can find the anti-vector frame, the origin's velocity as a function of joint variable velocities. So this dot becomes what? this dot becomes partial p partial theta times all the theta dot, theta 1 dot, all the way to theta n dot. So then what's the dimension of this guy?
3 by n.
Okay, this 3 by n matrix is actually the first 3 rows of partial g partial theta. Okay, and this is also called analytic Jacobian. So whenever you use not twist, but you only use part of the minimum coordinate, and so then that's become analytic Jacobian. Okay. So typically these two are related, and we're going to talk about how to derive them and what's their relation today. Okay, so let's directly start with the example. We have for simplicity, I gave or used exactly the same example as we used for forward kinematics. You should be familiar with this guy now. These two are robot, and as I mentioned before, I somehow tend to call this particular configuration is my home position. Okay, so current configuration will be theta 1 equal to 0 and theta 2 equal to half pi. Okay, that's what's shown here, but the 0 kind of frame is there. Sorry, home position is like this. Okay, and we are interested in let's see, this is B frame. I think I'm trying to use the same B frame as before. You can define arbitrary, you can attach arbitrary frame and at any point on the robot, and you can call that your frame of interest. And here I just attach it here, and this is XB head, YB head, ZB head. That's my coordinate system. Okay. So our goal now is to find the velocity of B frame as a function of theta 1 dot and theta 2 dot. So if these two joints are rotating, then B frame is also kind of moving. Okay, so the discussion, I somehow think it's more elegant or more easy for you to understand in the coordinate-free way, because to understand this concept, there's something really about physics, and the physics is really coordinate-free. Okay, and some part, the formulas is given you in terms of coordinate systems, and the complication often arises not because the physical inside is hard to understand, is really the complication caused by you choosing a particular coordinate system. You see what I mean? So whenever possible, you have to think about something without coordinate, then you choose one coordinate system to express the physics. I emphasize this quite a bit in the past few lectures. I think I'll keep using this as well. Okay, so I'm going to say coordinate free. I didn't say which coordinate system I express those vectors. I just say those physical vectors. First of all, they're physical axes, screw axes. I have two screw axes. Let's call that S1 and S2. Okay, this is my screw axis 1. This is screw axis S2. So these two refer to just physically that screw axis. It's not a axis. It's not only that direction and the line. It's really about a unit speed motion about that axis. Okay, so this you should know the physical meaning of the screw axis, really about unit speed rotation about that axis, or unit speed the screw motion about that axis. That's the meaning of this, right? Okay, this is for let's call it this for joint 1, and this is for joint 2. So I will argue that this guy S1 independent of joint variables theta 1 and theta 2. I hope everyone can see that this axis doesn't move no matter where the joint variables is, right? And but here this guy is a function of what? Liu Ben, S2 is depend on what?
Theta
Depend on
1.
theta, only theta 1?
Yeah.
Okay, depend on theta 1, but does not depend on theta 2. Okay, that's the physical quantity. I don't need to find a coordinate to say that. Okay, that's physics. Okay, so now I'm going to ask you, all right, what's the velocity or twist? Let's call it the spatial velocity. What is the spatial velocity of each link? Okay, it's link. First one, let's start from link 0. What do you think the velocity of link 0? Let me be more clear. The velocity of link 0. So then what is this guy? When theta 1 dot with, so suppose theta each has some speed, okay? I'm going to ask you what is the velocity of link. This is the link 0. This is the link 1. This is the link 2, okay? So then what is the velocity of link 0?
Velocity of link 0 is all 0.
All zeros, so it's 0, right? You mean all 0 means this is a 0 vector in R6, right?
Yeah.
It does not have any motion, it's 0. Okay, cool. That's a easy but a good starting. Okay. Then what about link 1? I'm going to ask Liuben, what do you think is the velocity of link 1?
The link 1's velocity, we can write the twist as 0. Yeah. Should I write the numerical?
No numerical, coordinate free.
Yeah, it's the S1 plus theta dot. Yeah.
S1 times theta dot. Okay, that's the definition of the rigid body motion twist and sorry, screw axis. So anyway, so you don't, for link 1, you don't care about how link 2 theta 2 is rotating, right? You only care about how fast theta 1 is rotating. And the rotation about the screw axis 1, this is 1, cause it's or the only reason that link 1 is moving, right? Link 1 is rigid body, right? It's rigid body, it has a velocity, and the velocity has a screw axis representation, which is S1 times theta dot. So where S1, as I mentioned before, is not really a physical axis. It's characterized by, it's really the unit twist velocity of the rigid body, which is moving about that axis. Okay, so then you times the theta 1 dot, that's the twist for link 1's velocity. I hope that's okay. Then I'm going to ask maybe Liuben again. What about link 2? Velocity.
Link 2's velocity. Yeah, it depends on theta, and
yeah,
it's the geometric Jacobian.
Yeah. Okay, let's do that by maybe coordinate free and some high school physics. This is velocity, right? So its velocity is link 2's velocity is that's a link 2's relative to link 1's velocity plus link 1 relative to link 0 velocity. 0 is something that doesn't change, right? It's okay. So link 2's velocity is composed of 2 parts. If link 1 doesn't change, only joint 2 is moving. So that's relative velocity of link 2 relative to link 1, which is what I mean here. And also maybe link 1 is also moving. So overall link 2's velocity is somehow a added vectors of these two velocities, right? if I want to say this way, what I mean is really link 2's velocity relative to the inertial frame, or link 0. Let's call in link 0 is the same. It doesn't move, so relative to link 0. So these two velocities, and the first one, link 2 relative to link 1. Suppose maybe link 1 is moving as well. Okay, I don't want to account for that motion for now. And the relative velocity of link 2 relative to link 1 is, Liuben, what is it?
The link 2 relative to link 1 is S2 theta 2 dot.
Yes, okay. So you think about link 1 doesn't move, or your inertial frame is on link 1, okay? And the link 2 has a motion only because theta 2 is non-zero. Theta 2 dot is non-zero, okay? And that's a link 2's motion is a rigid body motion, and it's twist representation is a square axis times theta 2 dot. And this means, physically just means rotating about square axis S2, with speed theta 2 dot, right? And the first one, link 1 relative to link 0, which is just what we called before, and this is S1 theta dot, theta 1 dot. So overall, if I want to write in the some kind of a nice form, I will say this is my S1, this is my S2, and times theta 1 dot, theta 2 dot, okay? And one thing is that I know this guy is constant. It doesn't change, all right? Doesn't depend on any variables, joint variables. And theta 2 is a function of theta 1. Fuzhen, what's this?
This is the geometric Jacobian.
Yes, that's the Jacobian maps what? The joint velocities to link 2 twist. So that's geometric Jacobian for link 2. But maybe we can do one more baby step, okay? What about frame B? For then, what is a VB? I claim VB is equal to
I have
V
a
of
question.
L2. Yes, go ahead.
So VL2 equal to VL2 relative to L1. This VL2 relative to L1, why it's S2 times theta 2 dot? I think
think about L1 doesn't move, only S2 the joint variable theta 2 is changing. So you have a non-zero theta 2 dot. So link 2's motion is a screw motion. Yes, go ahead.
But when we compute the L1 relative to L0, we think the L1 is moving. But
yeah, but that's
at the
not.
Same time, we compute the L2 relative to L1. This L1 didn't moving as
relative. Well, velocity is always relative, right? It's the same thing like if you have inertial frame here, and you have a point moving relative to this frame at some speed, the overall speed relative to the inertial frame, and this frame is moving as well. So it's this point, this point velocity is the point relative to this reference frame and the frame's velocity as well. If you don't get that, I think that's some physics. So there's a card moving, right? And there is a ball rolling on the card as well. And what do you think this ball's velocity relative to initial frame? Is velocity relative to this car, and also plus the car relative to initial frame velocity? Forget about the coordinate, it's just that.
Okay.
Okay. Yeah. So that's how we move on. Okay. So this is VB coordinate free wave, VB equal to VL2. For them, do you have any question about this?
No question. I think
Okay. Sometimes for some students, it may be because the key thing I emphasize maybe many times, maybe too many, is that twist or special velocity is not about a particular point on the rigid body velocity. Okay, it's not a velocity of some point or some portion of the rigid body velocity. It's a velocity or overall representation of that body velocity. If you talk about this body, these two are on the same rigid body. Okay, VB is rigidly attached to that body, so its velocity is just have one rigid body. Okay, so they are the same. So what we have is also this is S1, S2 theta 1, and theta 1 dot, theta 2 dot. Okay, so this is our geometric Jacobian. We can write it in a more Jacobian form. This is Z1. Overall, it could be dependent on theta. I will just write in the general form. In this case, it doesn't. The first column doesn't. This 2 dot dot in this case, and this guy is a first column of Jacobian, of geometric Jacobian, geometric. And the other one, this guy is the second column, okay? Overall, I can say Ji, the ith column, in this case, I equal to 1 or 2, okay? Ji is nothing but the twist or special velocity, let's say twist of VB of B frame when theta I is 1 and theta J equal to 0 for J not equal to I. So each column of Jacobian, in this case, the first one is this, right? Square axis 1. What does that mean? It's the, you think about this, right? You think about this case, theta 2 dot is 0. It doesn't change. It has a fixed joint position. So only theta 1 is rotating. Okay, and then this B will have a motion. And this motion, if you set theta 1 dot equal to 0, and the first column of the geometric Jacobian is just the screw axis of the first joint. Okay, or in other words, is the twist when the first joint has unit speed and all the other joint doesn't move. Okay, and similarly, joint 2 is sorry, the second column of Jacobian, geometric Jacobian also has similar meaning. Is that if joint 1 doesn't change, only joint 2 is moving, what is the end-effector velocity? Okay, that will be put into the column 2. Let's see. So far, this is a coordinate free. I think everything should be clean here. Then there's some kind of calculations that we need to compute in computer. That may confuse further some people, but at least I want you to fully understand the coordinate free concept. So we already know Jacobian now, okay? Each columns of the Jacobian matrix is just the screw axis of that corresponding joint. That's why it's really beautiful to think about everything in screw axis. So the computation part, so we need to work with one coordinate system. So for example, let's work with gyro frame, okay, inertial frame. Here the gyro frame is here. Let's call that frame 0, okay. And I'm not sure whether you still remember last time we know S1 in 0 in general, it could be dependent on theta, but in this case, doesn't, right? So equal to S1, everything is 0, theta is 0. So this is our definition is S1 0 bar. That's I also mentioned before. And this is when the screw axis of joint 1 expressed in 0 frame when all the theta are 0. And this is equal to what? If you remember, that's this screw axis expressed in 0 frame, and it's only have rotation, and we can pick Q on this axis. So if you remember, we're from last time, that is 0, 0, 1. So rotating the omega direction is along that along this z direction, and this one is 0, 0, 0. That's what we computed last time. And the S2, S2, let's see, S2. So this is given us the first screw axis. So S2 0 theta 1, that's a function of theta 1, right? And but in general, let's say if we want let theta 1 equal to 0, we have S2 0 bar equal to what? This screw axis. And when theta 1 is 0, it's screw axis just right here. And this axis, if you remember 0, 0, 1, I don't want to repeat the calculation here, is 0, negative IO1 is 0. From last lecture, let's accept that that's the coordinate of the screw axis 2 when joint 1 is 0. Okay. So now what we want is that, I'm going to ask Liuben maybe, S2 0, this is a bar, okay? If I want to tells you theta and the theta not equal to 0 in this case, what is this guy?
Equals to adjoint plus the adjoint matrix plus S2 1 S2 to 0. Yeah.
Okay, good. Yeah, got it. So let's do this case, all right? Let's say, how do we got S2 theta not equal to 0? So let's view this as a action operator thing. Okay, let's start from theta equal to 0. So which will be S2 0 bar equal to S2 0. If I don't have a bar, that means there's a theta equal to 0. Okay, this is a 0, this is a function 0. And this guy, how to move to theta equal to not 0? I apply a rigid body motion, which is, I call that operator T hat, theta 1. So it is rotate above screw axis 1 by theta 1. In this case, screw axis 1 is just a S1 bar because everything is 0 at this state. So how do I obtain the screw axis? Maybe if theta is moving, theta 1 has been changed to non-zero, that will change, right? So this guy will become, maybe this guy will move like that. Okay, that's the first arm. The second arm will be like that. And then the screw axis will change, right? If we think about this, that screw axis being moved by a rigid body operation, and the operation means rotate about first joint by theta 1. That's exactly this matrix. That's the operator matrix. And we know the rigid body operation on screw axis, you need to use adjoint of that operator T. So overall, I will have S2 0 theta 1 equal to adjoint T hat theta 1, where this is a matrix times S2 0 when theta 1 is 0. This is bar. Okay, this guy is 6 by 6 matrix. The rigid body operator is represented by a 4 by 4 homogeneous transformation matrix, right? And the adjoint is 6 by 6, and this guy is 6 by 1, and this is our new screw axis 6 by 1. So then this is clear to you?
Yes, it's clear to me.
Okay, good. Now numerical wise, I would say J of theta, that's geometric Jacobian. When I read like this, it's coordinate free. I didn't say which coordinate I want to express or write down the values of this Jacobian. If I say 0, that means I want to express this in 0 or inertial frame. And if I pick one, then I can have coordinates. Okay, I can have values. The first one is S1 bar 0. This is the first coordinate. Sorry, first column. And the next one is the second one is S1. What is this guy? This one is this, right? If I want to write, this is the second column, will be adjoint T bar theta 1, this 6 by 6 matrix times S2 0 bar. You should know how to compute every single column of this matrix now, right? The first one, we already know it is this number. Okay, and the second one, we know this is this coordinate, and we also know use S2 bar, S1 bar, I can find this T matrix because it's nothing but a matrix exponential. Of course, there's a function of theta 1, and we should be able to write down this explicitly as a function of theta 1, and then I can construct the adjoint operator, so I know this guy as well. Okay, that's a geometric Jacobian. Again, let's repeat. So far, we have learned geometric Jacobian, the first column, second column, is just the first screw axis and the second screw axis. The screw axis of first joint and the second joint, respectively, right? If you want to write down the coordinate of this Jacobian matrix, you need to pick a frame to represent it. If you pick inertial frame, okay, that's fine. Then columns of Jacobian depend on the joint variables. Okay. The first column is fine, does not depend on any joint. The second column depends on first joint. And you can view that as rigid operator operates, moves the second screw axis about the first joint by theta 1. Okay, so you have a adjoint operator. Hopefully that's clear for now. Okay, let's talk about general case. I think we don't need to say too much about general case now. It's just I think everyone can generalize in your mind now. So again, in coordinate free, let's say now we have n joints. Okay, we have n joints. We have n joints, not 2 anymore. That's the example. And the Jacobian, the geometric Jacobian, is nothing but this is J1 theta, the first column, J2 theta, all the way to J of n theta times theta 1 dot, all the way to theta n dot. Okay, and the ith column of this Ji, is the end effector velocity when robot is rotating about screw axis I at the unit speed, while all other joints do not move. Okay, in other words, if you let, of course, if you let theta I dot equal to 1 and theta, all the other theta j dot, this is dot, all the other theta dot is 0, then of course what you got is here is it will be just Ji of theta, right? You somehow pick the ith column by just decouple this motion, discuss those motions separately, or try to find their contribution due to each joint separately. If you only rotate joint I, and that gives you the Jacobian of the ith column, okay? And because of the definition of screw axis, it's nothing but screw axis. So in coordinate-free notation, Jacobian is nothing but square axis. I want you to somehow keep that in mind. When I ask you, when you think about Jacobian, you always, or at least geometric Jacobian, you always think about square axis. Okay, it's a several column depending on how many joints you have. And the ith column is just the square axis of the ith joint. The complication only arises due to you want to find where the square axis is, because the axis will be moved by the previous joints. Okay, I hope that's clear. So in coordinate-free setting, I can just write as simple as that, as insightful as that. So you don't need to memorize any formula. You should be able to speak this out very fast. Okay, and of course you can cheat, or you can find a coordinate that are very easy to express this physics. For example, the simplest way to write Jacobian is to use local coordinate. Okay, well, for example, the jth column is the the ith column is the ith screw axis, right? If I want to represent the ith screw axis locally using the ith joint, it is constant. It doesn't change, right? So this will be a constant, independent of any theta. Okay. This should be okay, because this equation, this is the physics. No matter what coordinate I use, the physics should hold. I can pick whatever coordinate to express this physics. And now I use ith coordinate, then that's become simple. But then each column have a different coordinate system. That's you typically write down a matrix. That means you choose one coordinate system to express all the joints. So in that case, typically we choose zero frame. That's where the complication can arise. Okay, so if you pick a fixed zero frame, then because in this case, if you want to Jacobian, you have to write a matrix J1, J2, right, all the way, and you want to use this same coordinate system to express them, then you need to do some change of coordinate, right? The screw axis or twist change of coordinate, we define it as this, right? If you remember, that's also related to adjoint. By definition, that's this, okay? So that's one way to compute the, how to say, the Jacobian in-frame inertial frame. Okay, if you still remember, this is the change of coordinate matrix for spatial velocities. And because, so that's basically depends on the relation of, this is what? This is the pose or configuration of frame, local frame I, relative to inertial frame. Let me go back to this example to just give you. So suppose last time I said I attach a frame like this local frame, right? I forgot which direction. Maybe this is the direction I use. This is x2 hat. This is a z2 hat. Okay, and this frame is attached to second body, so we move its second body, right? And locally around that frame, no matter what theta 1 is, S2 has constant coordinate. Okay, so S22 will be constant, right? And if you want to know S2 0, then you need to do a change of coordinate from frame 2 to 0. That's basically this T2 of 0 matters. And T2 of 0 also depends on what? Theta 1. And this is a forward kinematic relation. And we already know how to compute it. So in this case, I can do a change of coordinate to move everything to the same coordinate system. Okay, that's one way, but I don't think that's the most, if you want to do computation, that's, I think conceptually the easiest way for me. All you want is try to just change your coordinate so that you have a common coordinate system to express all these columns of the Jacobian matrix. In the book, in the modern robotics book, they have a recursive way. I think that this is also makes sense. What we have before is almost like that. This example is that. Let's work on that. Let's just use inertial frame. Okay, we want to write down the Jacobian in inertial frame or gyro frame. Okay. And initially, the first column does not depend on the joint variable, so it will be just the S1 bar. Okay, no matter what theta is, the first column, first screw axis doesn't change with any kind of joint variables. So that's the this case. And the second column, okay, the second column, S2, 0, theta, by our kind of notation so far, it depends on theta 1. That's the example, you already seen this, right? You have already seen this. That's a function of theta 1. And you view this, depend on what theta 1 you choose, that's almost like you move the initial screw axis 2, which is theta 1 equal to 2. Theta 1 equal to 0. When theta 1 equal to 0, this is guy, right? This is screw axis. And if theta 1 is non-zero, you apply a screw motion about first joint by theta 1 degree. So overall, you multiply by the adjoint. Okay, this is the formula. Okay, I don't want to do further too much. I will just do one more step. For example, when I equal to 3, then what is I theta 3? The third column. What this depends on? Of course, depends on theta. Depends on which theta.
Theta 1 and theta 2.
Theta 1 and theta 2. All right. And you can view this guy, how to obtain this guy is almost like you have a overall rigid body motion, which is composition of two rigid body motions, right? So basically you start from S3, 0, when the two joints are 0. That means S3, 0 bar, okay? And you move that axis got, you apply operator, okay, rigid body motion to it. You have a T2 bar, which is theta 1 and theta 2, that you rotate about first axis by theta 1 and the second axis by theta 2. The operation has to be applied, as we discussed in the forward kinematics case, backward. You first apply this guy, the screw axis 2 by rotate about screw axis 2 by theta 2 degree. Then you, because that will not, this operation will not change the screw axis 1. Then you rotate everything by screw axis 1 by theta 1 degree again. So overall, you have this operator. And if you apply this operation, then you move, somehow you change, you move the screw axis in space. So that becomes S3, 0, sorry. What you got is the adjoint of this T hat, theta 1, theta 2. This is 6 by 6 matrix times theta 3, 0 bar. Okay, this is 6 by 6 matrix again. Okay, so in general, we'll have this formula. Of course, you can look it up whenever you want, but should make sense to you. I don't want you to memorize it, but it should be able to, so every single symbol in this equation should make sense to you. Okay, the ith column of J is the ith screw axis. All you need to know now is how the screw axis depend on joint variables. Okay, and you can think about this as a rigid body motion. Initially, you know where the screw axis is, the ith screw axis. That's initially when everything is 0, when all the joint variables are 0. Then you apply screw motion of the previous joint to move it to the desired or the given joint position. That's almost like a rigid body motion. And you use adjoint of that composite motion to apply that to that screw axis. Then the screw axis new position in space will become this guy. Okay, hopefully that's okay for you. You should be able to compute, by the way. If I last time I gave a Drake tutorial on comparing how to do this screw axis stuff in Drake. You should be able to write code to compute Jacobian. As all you need to specify is the initial screw axis, the SI 0 bar. If you know that, then everything else can be computed numerically. I don't ask you or expect you to compute it by hand. Okay, let's work on an example. I think it's time. Let's take a break. All right, let's continue to finish this example. It's exactly the same example, but before I have a simplified version, I erase all this part. But now we have a 4-joint system, and that's a complete example. Let's work on that. Let's try to see what's the standard procedure to find or compute. In this case, not only find, it's compute, right? The geometric Jacobian. If I want to find Jacobian, it's just this Jacobian is nothing but screw axis 1, screw axis 2, screw axis 3, screw axis 4. Right, that's it. If you want to, because all of them depend on theta, potentially. So that's one formula for all case, right? So, but that's conceptually, if you want to work on coordinate systems and you want to find numerical values for them, you have to follow some procedure. Now, first of all, according to this procedure, right? First off, we need to find the first step. We need to find screw axis at home positions, okay? Or that means when all the theta is equal to 0. I think it's exactly the same case. I don't want to write them down, derive them again. So I will write down the first two at least. We work on the first two before. 0, 0, 0 as 2 bar equal to 0, 0, 1. I think this 0, negative I1, 0. Let's work on that S3 bar. Liuben, what is it?
001.
Oh, you can direct write on answer. Maybe let's work on some steps. This 3v3, okay? Where omega 3 is what?
001.
0, 0, 1.
Yeah.
I hope you can see that this is rotation. This rotate counterclockwise about this axis. This axis point to the in the inertial frame. It's 0, 0, 1. Okay, and then you need to find the V3 component that's only have rotation. You don't have the third joint. Okay, you don't have any kind of a linear motion along the axis. So it's only pure rotation. So that's what? Negative omega 3 cross Q3.
Yeah.
And I can pick Q3 on the axis. I pick here. No, sorry. You know that what we're computing is this axis, sorry. Screw axis here, right? So this is my Q3.
Yeah.
It's the same as Q2, right? It's just from the coordinate axis changed from L1 to L1 plus L2, right? So overall, I should have this one is 0, negative L1 minus L2, 0. Sorry, Liuben, is that right?
Yeah.
Okay, good. So overall, I have this guy is 0, 0, 1, 0, negative L1, negative L2, 0. That's my screw axis at home position 3. At home position. Now we need to work on S4 bar. Of course, the home position. What do you think? This one is, if you see the picture, that means you move upward. That's a linear motion. There's no rotation. It's just pure linear motion. So again, it is 4 and a V4. In this case, this is a pure linear motion. If you remember the twist, when we define twist, this is degenerate case. It's almost saying the piece is infinity. Okay, in this case, omega is 0, 0, 0. That's whenever you have a pure linear motion, the omega is 0. Okay, V4 is, Liuben, what is it?
V4 is 0, 0, 1.
Yes, along that axis, right? Along upward, the z direction. So this is the degenerate case. You cannot use this formula anymore. Okay, you just this will be just a normalized linear velocity in the direction of that velocity. So that's 0, 0, 1. So this guy equal to what? 0, 0, 0, 0, 0, 1. Now you have a bunch of numbers. I claim that's it. The rest is just formulas. Okay, the second step, you can just write down the geometric Jacobian in O-frame. It's a function of theta. It has 4 columns, right? You have 4 joints, you have 4 columns. The first one is S1 bar 0. Because this guy, I'm just write down the formulas for each of these columns. I didn't do anything new, right? The only thing I know for now is S1 is independent of theta. So I can pick whatever theta to compute S1. So that's S1 0 bar. The second column is S2 0 bar. That's our initial screw axis position. But it depends on theta 1, right? Theta 1 change, that axis move in the space. And the movement is characterized by the motion, this rigid body operator, which for twist will be adjoint T hat 1. Let's call that S1 0 bar. Okay, where I'm going to ask maybe Hongbo, what is this guy? Is Hongbo there? Or maybe Liuben?
Yeah, it's E to S1, S1 to 0. Yeah.
Okay. So whenever, as I mentioned before, you think about rigid body rotation matrix as action, it just rotate about certain axis by certain degree theta 1. Okay, that's where the exponential matrix exponential come from. All right, the second one is this is the second column. The third column is, sorry, I keep writing this wrong. This is 2, right? This is 2. And the I3 0 bar, that's initial, but now I need to apply 2 screw motions. 2 rigid operators, so I call it 2. Let me finish them together. I call it 3 operator, then 4 0 bar. Okay, where these 2 T2 head, it's matrix exponential as 1 0 bar theta 1 times S2 0 bar theta 2. Okay, and this 3 is 3 of them, right? It's E matrix exponential theta 1 bar 0, sorry, theta 1, and the times theta 2 bar 0, theta 2 times theta 3 0, sorry, S3 0 bar theta 3. So again, if you all you need to know is all these screw axis bar values, and after that you can define the operator, and then you can find the adjoint, and then you just write down like this. Any questions so far? Okay, that's the discussion for geometric Jacobian, okay, which is simple. It's very geometrically insightful, right? It's just the number of columns equal to the number of joints, and each column is a screw axis. You just need to find the screw axis because it's a function of previous joint variables. That's very insightful result. Then we can talk about analytic Jacobian. This is more algebraic, more numerical stuff, because that's really, you lose all the geometric insights because you need to find a local coordinate. For example, I can say x, as the initial example I told you, x can be x, y, z row pitch row, row pitch yaw, okay, or it can contain part of them. Okay, only contains the certain point or the origin of the anti-factor frame, or use different ways to write down to parameterize the anti-factor frame. So for example, x can be any task variables. For example, this guy can be Cartesian plus Euler angles, as I mentioned before. It can also be spherical coordinate, right? It doesn't matter. So it's, you pick a local coordinate you want, you pick some Euler angles or other angles to represent the orientation. Then you find out the analytical form of these variables. That's why it's called analytic Jacobian. Then you take derivative, just treat it as a pure algebraic or analysis problem, but you lose all the insight. Okay, so in this way you cannot obtain the geometric Jacobian. There's no way that you can pick some task variable and take derivative, you obtain geometric Jacobian, and that's not possible, right? So you somehow destroy the analytical structure, or sorry, the geometric structure of the Jacobian matrix. Okay, this guy Euler angle can be ZYZ angle, ZYX, many different things. The key is that you need to find let's call that x equal to g of theta. You need to find this function g. Then you take analytical Jacobian. This j analytical Jacobian is just partial g partial theta. Recall the geometric Jacobian we defined before. It's just the list of screw axes, okay? And actually, you can obtain analytic Jacobian from geometric Jacobian by multiplying some kind of matrix. This matrix really, there's no uniform formula. It really depends on the particular task variable you choose. So I say this can be found easily. I don't think it's easy, okay? It's pretty tedious. It can be found, okay, with certain parameterization. Let's work on this example again, the simple one. Just let you see some flavor of it. Okay, what I have now is, let's say, here is my 0 frame or S frame, okay? This direction, this guy is a top view, okay? This is my home position, right? And it's a top view of this figure, of this 2R robot. And this direction, if I want to use more precise, this is X0 hat. This should be Y0 hat. I hope you can see this, okay? From the top view, these two arms like this, and this is my X direction, this is my Y direction. Okay. Suppose I have a anti-factor frame that we are interested in. That's my B frame, right? This is my XB. This is Y of B hat, Z of B hat. Okay. If you from top-down view, I also have this attached here. I can see two arrows. This guy is XB hat. This guy is YB hat. Wasn't this clear to you?
Yes, it's clear.
Okay, all right. And we can use simple high school geometry to find out the coordinate of, let's call that this guy is my P of B. The point of this guy, okay? P of B. That's the inertial, the origin of the B frame. Okay, and this B frame origin has a inertial frame coordinate. This coordinate, let's see, the coordinate is given by this formula. Of course, overall, we ignore the thickness of this box. This is L0, right? So the two arms are at the Z coordinate are all the same, is all L0. So this P, the Z coordinate is L0. XY coordinate is given by these two equations. I hope that's fine. I'm not going to derive it. So overall, I will have PB0. That's my task variable. Okay, this is my task variable that I care about. I want to know the origin point, its velocity as a function of joint velocity. Okay. That's analytical Jacobian for that point. So I need to first find analytical expression for that point, which is given here, right? So, so I will just say this guy is PB of 0 equal to this vector, right? This vector. So if I want to find Jacobian, then let's say this is in this case, this will be my G of theta 1 and theta 2. So this guy dot equal to partial G partial theta, that's a matrix, times theta 1 dot theta 2 dot. Okay, in this case, this is my analytic Jacobian. In this case, analytic Jacobian. Okay, let's call that, in this particular case, J of A of theta. And this J of A theta is partial G partial theta. And you know how to compute it. It's what? It's partial G1 of theta 1. This is my G of 1. This is G of 2 function, 3 function, right? G of 3. That's the function also has a 3 component. This guy is partial G1 theta 2, partial G2 theta 1, partial G2 theta 2, and partial G3 theta 1, partial G3 theta 2. Is a 3 by 2. Okay, and I assume you can compute this, right? Let's pick one number to compute. Let's see. That's the first row. Let's say only compute first row. Partial G1 theta 1. Okay, you got L1 sine, negative sine theta 1 times theta 1 dot. And this guy also depends on theta 1. Let's have L2, negative L2 sine theta 1 plus theta 2 times theta 1 dot. So overall, you can factor out theta 1 dot. So what we have is negative L1 sine theta 1 minus L2 sine theta 1 plus theta 2. Overall, this whole thing, this first row, first column, times theta 1 dot, right? The second one, theta 2 dot. And this guy, with respect to theta 2, that's negative L2 sine theta 1 plus theta 2. Okay. This next one is L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. This guy is L2 cosine theta 1 plus theta 2 times theta 2 dot. Okay, and this guy is 0. It doesn't change with respect to, it does not contain any joint variables. So that's, well, we finished computing everything. This is our analytical Jacobian in this case. Okay, this is our J of A theta. Any questions? Now we want to point out the relation between this j of a theta with respect to the geometric Jacobian. I don't want to derive it in the most general case. I just want to show you somehow you can obtain this relation and how to obtain this. So let's say j of 0, the initial frame, right, of theta denote the geometric Jacobian. That we computed before. So that means VB of 0, okay, equal to j of 0, in 0 frame theta times theta 1 dot, theta 2 dot, right? And we also know VB in 0 is omega in 0 and V in 0. Let's denote that, right? I'm going to ask maybe Liuben, what does this mean?
This means we have a body fixed point currently coincide with the frame O.
Okay.
The velocity.
Yes. So it's the body fixed point velocity currently the velocity of a body fixed particle currently coincide with O, not with B. Okay. So that's a thing. Before I ask a question, people always think this the body field with B has nothing to do with B. Is depend on which reference frame you use to express the velocity of B. Okay, this B subindex means the velocity of B expressed in O. Okay, now I'm going to ask questions about what do you think based on twist. What do you think PB of O should equal to dot? Liuben again.
Is the velocity the bracket velocity
use twist. Use this twist. Okay. Yes.
Okay. Plus omega times O,
cross.
Yeah. OB.
Cross OPB, right? From
Yeah.
that will be PB coordinate that. Right?
Yeah.
So it's the velocity of this point, and this is my origin of the reference frame. O to this guy is just PB and O. Okay, that's my relation. And if I want to write it as a function of twist, okay, you know, A cross B equal to negative B cross A. So that will be equal to negative PB0 cross omega 0 plus V0. If I want to write in the matrix form, that's this guy is what? This guy is PB skew symmetric, right? So it's negative PB0 skew symmetric times identity is a 3x3 identity matrix times the omega O, sorry, small omega. This is V of O. Sometimes my notation is confusing, so this is a little V, okay? Any questions? And we know this guy is the twist. So I know this guy has a relationship with the joint variables through geometric Jacobian. So I can write like this 3x3 times J, the Jacobian, analytic Jacobian theta, because we already assume that's already been found. This dot, the 2 dot, okay. So we, through this way, we somehow find the derivative of this guy, which we computed here, right? Is equal to these two things times that. So overall, I have, this is my geometric Jacobian. In this case, this guy is also dependent on theta as well, right? So this is dependent, the J is also theta dependent. Overall, I have analytic Jacobian is some matrix times geometric Jacobian times the theta derivatives. again, let's go back to our general conclusion. The analytic Jacobian typically can be defined by a matrix, okay, times geometry Jacobian. And this matrix also depend on the configuration or joint variables. I use the simple example that we always use so far to illustrate how to compute geometry Jacobian. Analytical Jacobian, and how do they relate to the geometry Jacobian. This is all from the basic physics. And what I also want to emphasize is that this is conceptually easier, but it's less insightful, right? You need to find analytical formulas. You just take derivatives. You don't have those screw axis concept anymore. So each column of this is not a screw axis. Okay, is somehow coupled, screw axis coupled with the local coordinate you choose. So I can ask you another question. For example, I can say, how about I say there's a point, there's a point locally attached to that effector frame. Maybe this is a tool. Okay, this is a tool position. This is maybe I can call it Q. I want to know the tool coordinates or the derivative, right? I can also compute Q dot, and these you will have another formula like this. But geometry Jacobian doesn't change. Okay, it does not change according to what particular point you care about. It only depends on the which frame you attach your kind of B frame. Okay, which body you attach your B frame to. Okay.